Good morning, everyone. Welcome to this tutorial. So my name is Daniele Magazzeni, and together with Michael, Cashmore, and Luca Iocchi, we'll be giving this tutorial on AI planning for robotics and human-robot interaction. So this very morning, coming here, we had even one more motivation for why human-robot interaction is important, because we had the first experience of self-driving Uber by chance. And what is nice is that we discovered that at the moment, thanks to AI, two people for driving the car are needed. So the real truth is that AI is creating jobs rather than stealing jobs. But the point behind the joke is that anyway, there is no human-car interaction yet, right? Because you need to talk to humans. So one more step that is needed is for humans to be able to talk to the vehicles. A few disclaimers about this tutorial, just to set the context of what we are going to talk about. So first of all, planning a robotic is a rapidly growing area. And there are also many initiatives in the planning and robotics community to try to foster the synergy between the two areas. So workshops, special tracks, not just at ICAPS, but also in the robotics community, like ICA and IROS. And we also had a Dagstuhl workshop a few months ago, where we gathered together people from the planning and robotics communities to set challenges and goals. And so this tutorial is not meant to give a survey, but just to cover some of the aspects on the synergy between planning and robotics. Just to highlight, there is the Plan Rob workshop tomorrow. It's a full day workshop. Now I think it's the 4th edition, so you are very welcome to attend the workshop tomorrow. Now the second disclaimer is that one can use several formalisms to model robotics domains. And one can use several techniques for planning in robotics domains. So there is really plenty of techniques and formalisms. However, in this tutorial, we focus on what is domain-independent planning through PDDL-X. I'm saying PDDL-X because one message is that planning is not just PDDL, but it's PDDL, PDDL 2.1, PDDL 3, PDDL plus. Meaning planning is becoming more and more expressive, as we are going to describe in this tutorial. So again, here we focus on PDDL planning. Third disclaimer is that planning is actually a plural word. This is due to Malik Galab. And in fact, as you can see, the word planning is used in many flavors. Again, in this tutorial, we use planning referring to task planning. The last disclaimer is that this is a tutorial, and we agree to make it an accessible one, so an introduction. So, apologize if some of the things are already very well known to you, but the idea is to help people who are also new to the area. Everything we use in this tutorial, so slides, virtual machine, and demo, will be available in the tutorial website, which is hosted in the ROSPlan website. Okay, this is the outline for today. So I will start with an introduction and with some comments on why we think that PDDL planning is actually useful for robotics and for human-robot interaction. Then Michael will be introducing planning with ROS through the ROSPlan framework, and then Luca will continue talking about planning for human-robot interaction, and then we'll wrap up and close. There will be a break at 10:30. Okay, so let's start on why PDDL planning is useful for robotics and HRI. So first of all, let's start for where it's not useful in our view. First of all, it's not useful planning if you are dealing with single or repetitive tasks. So if you are working with manipulation or grasping, you don't really need task planning, right? People in robotics are already very good at doing this. Similarly, if you're interested in safe navigation, you don't need PDDL planning because sampling is already very much mature, and people are doing that very, very well. So you don't need PDDL planning in this kind of scenario. However, PDDL planning is really useful when there is room for optimization at the task level. And we will see some examples in the rest of the talk. Another disclaimer, please feel free to interrupt, to ask any question, or to raise any comments during our talks. Okay, now these are some of the points why we think that PDDL planning is useful for robotics, and let's go through, briefly through each of them. First of all, planning is more expressive than what people used to think. So planning is not only a block word. There is much more expressive power. And this is an overview of the family of PDDL languages. Again, this is for those of you who are new to the field. PDDL is just for expressing Boolean things, so predicates, true or false, but since then there have been extensions to PDDL in order to add numeric effect, to add temporal constraints, to add preferences in PDDL3, up to PDDL Plus that allows to model hybrid systems, meaning systems where you have discrete change but also continuous change described by differential equations, so you can model also very complex domains. And at the same time, there have been a proliferation of new planners able to handle larger classes of PDDL. Where planning sits with respect to control, now planning is here on the right hand side, and you see different tasks involved in robotics, and for each of those tasks you see a different kind of uncertainty. So for example, at the planning level there is ignorance, meaning that you don't know, you don't have complete information about the initial state, for example, right? And then when you move toward the left-hand side, you start working with execution monitoring, and there the problem is that there is uncertainty, meaning that you don't know what's going on in the environment, for example. And then at the control level, you have inaccuracy, because, for example, you cannot assume that the actuators are exactly precise, right? There could be inaccuracy again. And then finally, at the sensing level, you have noise. So you cannot expect that your sensor will actually capture the real environment with full details. There is noise. Now, planning, again, if we start with simple forward search planning in a classic domain, you have states and you have transitions between states. So you have action that tells you how you move from one state to the other. When you add time, it's like actually an additional dimension. And so what happens is that in single states, you can spend a given amount of time, and during this amount of time, things can change. And then you can move between states after you spend some time in the single states. So time adds a dimension, adds complexity, but also adds expressive power. What planning in hybrid domains is, again, I'm spending 3 slides on this just to make you aware of the ability of PDDL to also modeling hybrid systems which are much more expressive than just classical planning. So hybrid systems are systems where we have discrete change and continuous change. They are very useful to model real application, because in real application, many times it happens that you do some discrete change, like, I don't know, opening a tab, and this triggers a continuous change, water flowing and so forth and so on, right? And many times, particularly when you have flows of energy or fluids, think about the oil and gas domain, for example, you need to be able to reason with this continuous change. And a very simple example, how you model the fact that you have a ball, at a certain point you stop having the ball, so the ball falls, right? So this is an example where you have a discrete action, not holding the ball anymore, and then that triggers a continuous change of the ball falling. So what happens is that as soon as you have the discrete change, holding the ball, not holding the ball, there is the continuous process starting. Now, how we model this in PDDL, again, this is a tutorial, so we want to teach something for those of you who don't know this. So this is an action in PDDL. So the preconditions are that I'm holding the ball, and the only effect is that I'm not holding the ball. So this is a discrete change. Holding the ball is true, and then it's false. This change, in turn, triggers the execution of the process. Now, process in PDDL Plus are the construct used to model continuous change. And processes are triggered as soon as the preconditions are true. So it's not that the plan, you will not find this process in the plan. In the plan, you will only find the action of releasing the ball, and then this process triggers as soon as the preconditions are true. And the effect here is that when the process starts, changes the velocity and the position of the ball over time. Again, this is a continuous change over time. And then you want to model the fact that at a certain point the ball can bounce, right? And this is called event. So in PDDL Plus, we introduce processes and events, meaning that processes are used to model continuous change. Events are used to model changes in the environment. So this is not the action of the plan, but it's something that happens because of change in the environment. In this case, you have the fact that the ball hits the floor and then bounces. So it's an event. If you can think of events like the word version of the actions. not action decided by the planner, but by the environment. And then you can have an action for deciding to catch the ball, and the preconditions here are that you want to catch the ball in a specific position of the ball. Suppose you have a robotic arm, right? So you can plan with these things, processes and events, and this is a very simple example of a plan. So these are the only actions you see in the plan. Of course, the first action triggered the process, and then there was the event of bouncing, and then the action of the plan for catching the ball. I mean, in classical planning, it's easy to see when what a plan is doing. In hybrid systems, it's more difficult to check that that plan is valid, right? Because you need to reason with the differential equation and so forth and so on. So the community has got this validator val that allows you to check the validity of the plans. And this is an example of the report provided by val. So you give in input to val the domain description, the problem file, and your plan, and val provides you a full validation of the plan, showing that it's valid according to your domain. Okay, and also val, just for your information, also provides you a LaTeX representation of the continuous dynamics of variables. So it's also a very useful debugging tool, as well as a tool for documenting what's going on when you execute your plan. And these are a set of PDDL plus planners. So as you can see from the years, it's a growing area as well. So more and more people now are looking at PDDL plus, trying to create planners for PDDL plus. The bar here is because all the planners above are strictly PDDL plus planners, so they can handle PDDL plus semantics. The planners below the bar cannot handle PDDL plus as it is, however, they are powerful enough to handle hybrid systems. So perhaps you need to translate the language in their formalism, but then you can use them. One more example, which is very recent, but it's quite realistic. So the idea of using planning for the vertical takeoff of these aircraft. And the problem here is that you need to decide the position of the fans and rotors. So what you do here is that you have an action for starting the engine, and as before, you only have a very simple discrete change that in turn triggers this ascent process, right? Which is a continuous process modeling the continuous change of the position of the aircraft. And the way you can interact with this process is that you can have this action, increasing angle, that determines how the aircraft moves. So you have the process in the middle, always active, and the action you use for changing how this process evolves. And of course you have an event crash that you want the planner to avoid, otherwise the mission fails. So events are also used to prevent the planner for, having a bad behavior. And then you have, this is the interesting point, so you have a process, wind, that clearly models the environment. Okay, this is a simplification, but can be made more realistic, and it influences the position of the aircraft. And finally, you have this time initial fluence. So time initial fluence are used in PDDL plus to model what happens over time. So here we are saying that at time 5.0, the wind in the x and y directions is given by those values. And then at time 9.0, it changes to new values. So you can use time initial literals to describe in the initial state the prediction of what's going to happen in the future. And this can, impact on your model. Okay. Next, this was just to give you an idea of the fact that PDDL is more expressive than what many people used to think. It's not just box word in a sentence. The second thing why planning can be useful is because there is room for calling, the so-called opportunistic planning. Now, this is an example for a project we've been working on the underwater robotics. It's called Pandora. And the problem here is persistent autonomy, meaning that you want the AUV, the autonomous underwater vehicles, to be in the ocean for days or weeks without human intervention and doing a set of tasks. In particular, the AUVs are used for these inspection and maintenance missions that involves these kind of activities. So inspecting structures, cleaning structures, and turning valves, so also manipulation tasks. And there are opportunistic tasks. Now, in AUV mission, you have to handle many tasks. So you plan for a long horizon mission. And the point here is that it might happen that you have high utility, low probability opportunities, meaning that while the AUV is operating, is running the mission, there might be something that you discover and things that are very important to handle. In particular, in the underwater domain, something which is very important is to discover chains, right? These are some examples of problems had in the past where, for example, we're supposed to have a boat linked through chains to some other structures, but then was discovered that actually all those lines were missing, right? So they were not connected as expected. So it was very important to have AUV that while running the mission, if the AUV spots discover a chain, it's very important to follow the chain to check if there is something wrong. For example, the boat is no longer connected. Okay, so they are low probability, meaning that it's not so likely to happen, but if it happens, you really need to take action and follow the chain. And this is called opportunity because you have a plan, and the fact that you have to follow this chain is not part of your plan. It's an opportunity, meaning that you don't know it in advance. You discover this opportunity and you want to follow the opportunity. Now, one way you can plan with opportunity is that, so this is a set, suppose this is your plan, and in temporal planning, you have durations for actions, right? So you plan when action starts and the duration of the actions. Now, what you can do is that you can build a robust plan using an estimate duration which is longer than the mean. So, for example, you can use the 95th percentile of the normal distribution. This gives you some room for saving time while then you execute the plan, and the time you save can then be used to fix the opportunity when you spot it. Okay, so the opportunity looks like that. So you have the initial plan, the main plan, but then it happens that after executing action 1, you spot the opportunity, and then you can decide to deviate for the original plan to, exploit the opportunity, for example, to follow the chain, and then at the end of the opportunity plan to get back to the main plan. Okay, and this process can also iterate and have opportunities in the opportunities, because remember that we are talking about missions of many days or even weeks, so there is also room for discovering a lot of opportunities. Now, clearly one obvious question is why we just don't replan. So after action 2 we replan all the mission from scratch instead of planning only for the opportunity plan and then planning to get back to the initial plan. So clearly the problem with replanning is that the problem becomes more difficult to solve, because now you have more goals, the original goals plus the opportunity, and you have less time. So planning is difficult. And however, the benefit of replanning is that you can decide to use the time you have to use it later on, rather than exploiting the opportunity right now. So we did some tests just to show the benefit of opportunistic planning, and we gave 10 seconds for the opportunistic planning, so for planning only for the opportunity and then get back to the plan, and we gave much longer to the time for replanning, even if in real execution you cannot give 30 minutes to the AUV to replan, it's too much. However, for testing it, we gave it a lot of time, and interestingly enough, we discovered that only in 2 cases, by complete replanning, you are able to find a better plan than only planning for the opportunity. And this is very interesting, because it means that in practice, in real execution of plans, it's really a good way to go, exploiting the opportunities. Okay, so we did some more tests, but the idea is that, in many real applications you need to handle just the opportunity rather than replanning from scratch. An important point here is that in the AUV domain, opportunities are basically every time you spot a new object or a new chain. However, in many other scenarios, particularly with drones, for example, opportunities can also arise for supervisor requests. So the supervisor tells you, I want you to achieve this new goal. And then you need to understand whether you can deviate for the current plan, solve the new goal, and then get back to the plan. So opportunistic planning, I think, is very important when dealing with the real applications. There will be a talk on Friday in the journal track of the main conference. Okay, Quickly on something, another reason why PDDL planning is useful, which is strategic planning. And here is that still in the domain of underwater robotics, but this is generalized to many other domains where you have long missions, right? So you need to plan for long horizons, and as we all know, planning with long horizons is difficult because the state explosion is huge. Moreover, you have time windows, meaning that there are tasks that you have to do only on specific time windows, and you need to plan making sure that those tasks will be done on those time windows. For example, sea-based facilities need to be inspected at certain intervals, as well as, for example, recharging a UV. You cannot recharge whenever you want. There are time windows. Also, communication windows in the UV domain, but also in the satellite domains. It's a very common problem. Now, as I said, current planning systems struggle in finding long plans for the state explosion problem. One possible solution is to decompose the problem into strategic and tactical layers. What you do in this case is that you have first a strategic layer where you have a high-level plan that takes into account all the time windows, and then you have a tactical layer where you solve the single tasks so that the strategic layer will handle the tactical plans. Now, I know that it might look similar to hierarchical planning, but the reason why it's not hierarchical planning is that because in hierarchical planning you have the tactical plans beforehand. They are fixed. While here the idea is that you use planning back and forth between the strategic and tactical level to create the tactical plans. As I said, these are the tasks involved in the underwater robotics, and this is an example. I mean, this is a quite high resolution simulator of AUV, also done in ROS plus visual plugins. So these are the set of tasks that AUV has to perform, and the idea then is that you start by clustering, meaning that you group together geographically all the objects that are of interest, and for each of them a jump off point is created, which are the points where the AUV needs to approach the area of the single cluster. And then what you do is that for each task you create, using PDDL, this is PDDL 2.1, you create a tactical plan for a single mission, and for each tactical plan you take note of the energy consumption and the duration. This is the information that is feedback to the strategic layer. And the strategic layer, what you have is that you have the time windows now, and you have all the tactical plans, and the task for the strategic layer is to take all the tactical plans created before and to fit these tactical plans into the time windows in order to have a consistent plan. This allows scalability for missions where you have long horizon plans. Okay? And this is how then all the, you have the movement of the AUV to jump and to start any new cluster and handle that. Any questions so far, or can I move on? Okay. One more reason why we think that PDDL planning is useful for robotics and HR is that explainable planning, planning is explainable. Now, many people are now talking about explainable AI, so there is the DARPA challenge, many people talk about that. However, many people talk about that from a machine learning perspective, the need for explaining neural network. Our view is that planning can be an interesting contribution in the domain of explainable AI, because planner can be trusted, planner can allow an easy interaction with humans, and planner are transparent. At least the algorithm or the process used by the planner is clear and understood by people who program the planners. Okay? Of course, we still need to work on XAI for explaining neural networks, but still planning can be useful. Now, what is an explanation for planning? What does it mean for a planner to explain the plans to a human, right? Also in terms of human-robot interaction. So first of all, explainable planning is not explaining what is obvious. Of course, in planning, we have planners working with heuristics, right? But to the question, why did the planner do that? You cannot just answer because the heuristic value of this action was lower than the other one. This is not an explanation. This is something obvious, right? Rather, a request for an explanation is an attempt to uncover a piece of knowledge that the questioner believes must be available, so I would like to know this, but it's not available. So it's not the obvious to explain things in planning. There is a lot of work related to explainable AI planning, mainly in the plan explanation, plan scalability, and there is transparency and autonomy. And I mean, there are many people working on this. So there is a lot of things we can build on for achieving explainable planning. In particular, I'm not talking about this because Manuela will be giving the talk, but in robotics there is this now research area of transparency in autonomy. Some of the things to be explained, these are some of the questions that I think when you work with robots, right, and so the supervisor has to accept the plan for the robots, these are some of the questions that the supervisor would like to understand. Why did you do that, or why didn't you do something else that I would have done, right, looking at the planner? Or what is what the planner is proposing more efficient, safe, or cheap than something else that I would have done, so different metrics. Or when executing plan, two important questions are first, why can't you do that, or why do I need to replan at this point? So when you are executing the plan, you don't want to replan every time things are different. You want to understand when it's needed to replan, and similarly, why do I not need to replan at this point? Meaning that you don't want to use a naive approach of continuously replanning. You want a way to understand whether your plan is still valid or you need to trigger a replan. An illustrative example. Okay, let's take the rover time domain, which is one of the benchmark problems in temporal planning. And this is the plan found for one of the problems filed. So you have two rovers which have to navigate between waypoints and take some sample, take some image, and communicate the results of what they are doing. That's the duration. So one question could be, okay, why did you use rover 0 to take the rock sample at waypoint 0? That it's a 10.5. Okay, that's one question. Now, one answer could be so that I communicate data from the rover later, right? So this is the connection between the two actions. I mean, but this is a naive answer, right? Because again, it's quite obvious. If one looks at the plan, it's pretty obvious that if you want to communicate through the rover 0, that rover must have done the observation, okay? So it's not an explanation, it's something very obvious. So actually, another way of looking at this question is, why didn't rover 1 take the rock sample at waypoint 0? So why didn't use the other rover, for example? And in order to explain this, one way is that you want to, one algorithm to answer this question is that you run the plan up to the point where the human wanted to suggest an alternative, so use rover 1 instead of rover 0, and then replan and see what happens. So in this case, what we did is that we removed the ground action for rover 0, so that the planner cannot use rover 0 for taking the rock sample, and then we replan, and what we find is a plan which is longer than what we had before. So this is a step forward in explaining why rover 0 was better than rover 1. However, it's not still completely satisfactory, because now I look at this plan, and as you can see, in this new plan, rover 1 is doing everything, right? So the question is, but why are you only using rover 1 for doing everything, right? Can you use rover 1 and rover 0 in order to improve this plan? So what we do is that then we recline the plan to contain at least one action that are rover 0 as argument. So we force the planner to say, show me how you can improve this plan by also using rover 0. But this is what the planner finds, which is basically the previous plan plus some useless action with rover 0. So it's not actually able to improve the plan with rover 0. So the answer would be, there is no useful way to use rover 0 for improve this plan. Now, actually, this example goes, it's longer. There are other questions and refinement on this question. They are on the papers. But this is just an example of how you can play with the planner or with your model in order to explain why this plan is better, more safe, robust, and so forth and so on. Another example at execution time. So the point here is, you have a plan, you execute the plan. During execution, you want to know, you want a way to understand whether things are going well or you need to replan. And this is a very important point in robotics and in plan execution, because you don't want to continuously replan. as well as you don't want to discover that you need to replan only when it's too late to actually save the situation. Okay, this is what I just said. So one approach, I mean, Michael will go over this later, but the idea is to use the filter violation, which, for example, is implemented in the ROSPlan. The way it works is that you have a plan, and then ROSPlan creates a filter that considers all the preconditions of the actions in your plan. So, for example, if you have this action, navigate from between two waypoints, and the precondition is to have the two waypoints connected, then for each action in the plan, suppose you have this action in the plan, then this predicate is added to the filter, meaning that given that you have that action, navigate from waypoint 3 to 5 in the plan, in order for your plan to be valid, the two waypoints must always be connected. You do this for all the preconditions of the actions in your plan, so that as soon as some of those preconditions in the filter are violated, you know that you need to stop and replan. This is an example for a UV domain again. So longer plan, and here you see in blue you have connection, the roadmap connecting all the waypoints. In yellow is the trajectory of the AUV. What happens is that at this time point, basically the AUV observed that there is an obstruction here because the map originally was not as accurate as expected. So you realize that that action in the plan can no longer be executed. So you discover much earlier in the plan that your plan is not going to be valid anymore. So you can trigger replan in time and, you know, improve the situation. Okay, I'm going to finish my part just to introduce another issue with planning, which is planning with uncertainty. Now, even here, you know, planning can handle uncertainty. However, there are a number of assumptions that you need to make. You need to pay attention, right? So, first of all, action may fail or succeed. So you cannot assume that everything will be successful in the execution of your plan. The effects of an action are not always deterministic, meaning you can have no determinism. You don't know whether the outcome of the action will be A or B, but you can model that. Of course, the environment is dynamic and changing, so think about the AUV domain. There are currents, there is visibility that changes, so you need to handle this kind of very dynamic environment. And particularly in human-robot interaction, Luca will talk more about this, but humans are unpredictable, so you cannot expect the behavior of human to be fixed, right? And you have to take this into account. So, in a sentence, the domain model is always incomplete as well as inaccurate. So, we will talk more about human-robot interaction, but if you have robots interacting with humans, you really have no reasonable assumptions on what the humans will do, right? So here you have humans interacting with the robot, also having a dialogue with the robot, and really it's not easy to predict the behavior of the human. I'm stopping here because there is Luca also offering a demo on this topic later on. And so what you need in this case is no longer a fixed plan that assumes that everything will work and nothing will change, but what you need here is a conditional plan where you have branches, and so that at the execution time, the plan will decide what to do based on the observation of the behavior of the humans or on the behavior of the environment. I stop here. Are there any questions before we move on into ROSPlan or comments?
Slides are available, right?
Sorry?
Slides will be available?
Yeah, sure.
Yes.
As well as the demo and everything, basically. Okay? Michael, you want to change the... Okay? Because now the next step is ROSPlan. Just to introduce this while Michael while working on planning with robots, we realized that many people in robotics use ROS, the robotic operating system. So we realized that in order to talk and to work with ROS systems, you need an agile way of using planning with ROS systems. That's why we developed ROSPlan, which is a framework that allows the use of PDDL planning with ROS. And Michael is going to talk about it.
I have also one very small disclaimer, which is in the same way that planning is not just PDDL, planning for robotics is not just ROS, but ROS is what we know, so that's what we'll be focusing on today. The outline for my section is going to be a very brief introduction to what ROS is and how we use it, and then I'm going to focus on plan execution. So Dan's been talking about how we use the planner to generate plans. I'm going to be talking about then how we actually manage to execute these plans on board a robot, and that to me is just as interesting as generating them. To do that, I'm going to just lightly cover a number of issues that arise during plan execution and solutions that we have to these issues, without going into too much detail. Oh no. Okay, it looks like it's going to want to automatically move the slides forwards. We'll deal with that. That's an execution problem.
Yes.
All right.
Keeps you on time.
Yeah. All right. To do this, I'm going to start with a very simple plan execution system that we can build in ROSPlan. And as I introduce each problem, I'll gradually make the system more complex and finish with a couple of examples we have from applications. Okay, so ROS is a framework for coding robotics applications. A ROS system is comprised of a set of processes which are encapsulated in what's called nodes that can run on a single platform or distributed platforms and communicate by passing messages. Messages can be passed on topics in just a many-to-many communication. Any node can publish to any topic that it likes or subscribe to any topic, or as services, which are more like remote procedure calls. These will block the service until a response is sent from the other node. ROS is quite useful in that there are already a large number of tools and software libraries available, and because it's such a modular system, it's very easy to combine these tools together and create a functioning system very quickly. And it's this ethos that we try to also replicate with ROSPlan. So an example of a ROS system here, there's these circles and nodes which are running, and the square is the title of a topic. Here we have a teleoperation node, which is just listening for commands from a keyboard, publishing these to this command velocity, which is being subscribed to by a simulation node, which is simulating a robot. In this system, there is actually no robot. It's just a simulated robot being driven by a keyboard. So there's no AI, there's no robot, but it's a ROS system. All of these nodes can be launched in a number of ways, but the most basic is just to have a launch file, an XML formatted file, which specifies all of the arguments for this node, for each node, and boots them up. I'll return to how we use different launch files later, but in practice this is where you place all of the parameters for your system and decide what it looks like. Okay. One kind of message, this is one ROS library I'd like to just talk about in slightly more detail, is the ActionLib package, which standardizes a way of passing messages that encapsulate a single task that the robot should perform. It will generate a topic name for sending goals to this task, for the task controller to return feedback, and then return a result when it's completed or when it's been aborted. Because we're doing task planning, this package is going to be very useful. One goal message in the ActionLib style might look like this. This is from the MoveBase library, which is used to navigate robots, usually ground-based robots. And you can see the message is it's a serialized object, in this case storing the desired position and orientation of the robot. So you would send this message over the goal topic, and whatever controller is waiting on the other side or subscribed to this topic will pick up the goal message and begin to execute it. Right, that's it for a basic introduction to ROS. Now I'd like to talk more about the plan execution. So any time you've been in a project and you're interested in generating plans that are to be run aboard a robot, or you're interested in implementing the control of the individual actions inside the plan, you probably had to implement a very quick executor just to send those actions to the robot and watch it happen. And this is the most simple way of doing that, where you have you've got your domain file, you have your problem file, you want to pass it to the planner, and then you want to take the actions in the plan and send them one by one to the robot controllers. This is where we'll begin. As I said before, I'm going to try and cover a number of different solutions in plan execution, because this is as widely studied a topic as planning itself, and there's no way I'll be able to cover anything in great detail. But the references are here on the slides for later, and there are more later. Okay. So in this case, these red boxes are nodes that you can set up in ROSPlan. So in ROSPlan, there is a node that you can launch which accepts a domain file and a problem file. You can set where those files are as parameters in the launch file, or you can pass them on topics. And it just interfaces with the planner. So it's just a way of hooking a planner into a ROS system. The plan itself is then published from this node as an array of action dispatch messages. And these just correspond to the PDDL syntax of action name and parameters. What's more interesting to me is this plan execution box. So how could that work? The first step is to say, well, what about if we just do a very simple sequential execution of the actions? We have this array of messages. We take the first one, we send it to control, whatever controller is implemented on the platform, and the control will achieve that action. This step itself is not trivial, because the PDDL action doesn't contain all of the information that the controllers need in order to actually achieve that action. So there has to be some kind of interface here which will transform the PDDL symbolic action into a concrete ground action here. So for example, this go to waypoint 0 action in the PDDL plan would look like this in the action message. You can see here the parameters, the duration, and dispatch time. But when we want to convert that into the move-based goal I showed you earlier, we need to know what are the x, y, and z positional coordinates, and what's the orientation that correspond to waypoint 0. And that information has to be somewhere in the system. But assuming we have a nice interface here for each type of action which performs this making concrete of the actions, then the executor needs to wait for the action to complete, wait for success or failure feedback, and then dispatch the next action. And often, hello?
When you say waiting for action to complete, do you have an explicit precondition, post-condition for actions? Because in practice they turn to fail a lot of time in very interesting ways. And as we discovered, one of the most important things, so to be sure before you even start moving from point A to point B, be sure you are at point A to begin with, and do something if you are not. And once the system claims to have completed the action, have some sort of independent verification that you are indeed at point B. Is the representation of that sort of thing anywhere in the system?
Not the current one, but I'm just about to move on to the pretty much exactly what you said. Well, there are all kinds of problems that come up. I like to talk about it as zombie-like behavior, where you're watching the robot acting in a way that just appears mindless. The first reason that can happen is that an action fails and the recovery is handled by the control, which, I mean, you do want a nice, robust control. The issue there is that when we're modeling the PDDL domain, normally we model the action, precondition, and postcondition and duration in a way that represents what happens when the action succeeds. Like, this is what the action does. When the action fails, or begins to fail and control has to perform some kind of recovery procedure, then the behavior of the robot is no longer what was modeled in the PDL domain, and all sorts of strange things can happen. The other thing that can happen is that the plan will fail, but the robot doesn't notice. That's more like what you were talking there, where an action has failed, but the action doesn't realize that it's failed. And the plan hasn't realized that the action's failed because it reported success, or we didn't check its post conditions, and the robot continues acting, driving uselessly into a wall or down some stairs. I'll cover the first part to begin with. So, in the worst case, an action might never terminate. You might have a navigation action which, until it reaches its goal position with a very fine threshold, will continually try to reach that position. Or you might have a grasp action that when it fails, it continually retries. You may end up with a robot that never gives up, and you want it to, at some point, to give up and report that the action has failed. So if we desire the robot to act without a human coming in and killing the system and recovering it, at some point the action must be preempted. It must be interrupted and stopped. If this is the case, then we have to be able to replan and continue acting. But because the control handles some recovery behavior, the state might not be what the planner expects it to be. So we need to keep an up-to-date model of the state in order to replan from what the environment currently looks like. So we have this new node in ROSPlan we call the knowledge base, which is just there to store a PDDL model, a PDDL problem file, which can be then updated continuously to store an accurate copy of the state, as accurate as we can get. And that would be used as the new initial state when it's time to replan. The interface to this is also just ROS messages to hold PDDL data. So this is just to store predicates or numerical functions into the knowledge base. Finally, this allows a new node to be generated which will take on topics that you specify in the launch parameters, a new problem instance and the domain file from this knowledge base, and generate, just the domain file and all of the facts, and generate a PDDL problem instance in one of the flavors of PDDL to be passed to this node, the planner. I mean, the greatest benefit of this is you no longer have to keep writing your own problem instances, which I think is ideal. Not so fast. The model also must be continuously updated from the sensor data, from what the robot can see. In this case, just like we had interface nodes which took symbolic PDDL actions and converted them into the sort of ground truth goals for control, there's going to have to be some interface that reads the sensor data that's been processed and converts back into the symbolic model and stores it in the knowledge base. So in this example, we have something that's subscribed to the odometry data of the robot and performs very simple which waypoint is the robot closest to, and keeps that up to date in the knowledge base. Putting all that together, we started with this simple thing, and now we have a number of new nodes and a slightly more robust system. If you downloaded ROSPlan and launched one of the demo launch files, this is the kind of setup that you start with. But I'll describe it a little bit more after I've talked about the other kind of bad behavior, which is plan failure. I have this kind of example of some bad behavior. Oop. I think the robot falls over at the end of that, but I'm not interested in the falling over. Yeah, plan success. All of the actions executed without fail. But obviously the plan didn't succeed. I imagine that the plan was for the robot to be turning the valve. But it wasn't the turn valve action that failed, I think. And I wouldn't even say that it was the navigation action that failed. If the navigation action had a threshold and it was within the goal threshold of its of the position in front of the valve, then that action didn't fail either. Instead, there was some kind of diagnosis missing at a higher level, at the plan level. And this kind of diagnosis, this pre and post condition checking, has to be present in order to determine whether or not the plan is still succeeding. As Dan was talking about earlier, this kind of diagnosis will also be checking whether or not the plan is going to fail sometime in the future and stop the robot from continuing to execute the plan for a long time without purpose. Especially if you're in a domain which includes dead ends, this is important. One key point is that the success or failure of an action can sometimes be highly dependent on the context in which it's being executed. If the navigation action is to be followed by a turning valve action, then the accuracy of its final goal position is very important. But that's not always the case. And it's not possible for all of the actions to self-diagnose themselves within the context of a plan. That's why this kind of diagnosis has to take place at a higher level. So going back to this diagram, that's why this blue arrow from the knowledge base is not just directly piping the information into the problem generation, but is actually kind of touching everything here. Because the dispatch is also performing validation continuously. I have an example. That's weird. Anyway, I'll read the text at the bottom for you. We were running this application in the diving training center at Fort William, in which this AUV, this Nessie from the Heriot-Watt University, was meant to navigate around these two concrete pillars and inspect the iron pipes on each side. It generated the probabilistic roadmap, as Dan showed previously, and calculated that this path would be the best to inspect all of the pillars, the most difficult two being the facing sides of the pillars. Here it says that after spotting an obstruction, there we go, it should replan immediately. Because what happened was we placed an obstruction in the middle, and as the robot began to move around, it could see that there was an obstruction there after the first inspection, and was able to replan straight away, rather than spending a lot of time moving to the other side and performing all of the other inspections, only to then have to move back again in the best case. And in the worst case, just taking sonar readings of the obstruction and reporting data that was completely useless. So now we have this system which automatically generates the problem file, passes this to the planner, passes it into ROS messages, and then begins sending them one by one to the platform, waiting for success or failure to be reported. All the while, it's validating against the model to make sure that the plan is still valid. And when the plan is invalidated or an action fails, it's able to regenerate the problem instance from what the current model looks like according to the sensors and replan. Right. So that's the summary of very simple sequential dispatch. I'll now move into the second problem, which is very simple temporal dispatch. So as soon as you have a domain or an application in which there are temporal constraints and time is important, you run into problems with this kind of execution. As soon as we wanted to include another AUV, we had the same issue. So if we were to try and dispatch the actions one at a time, waiting for the last one to complete in this scenario, we would get this staggered movement where only one of the AUV moves at a time. So the first one would move up, the second one moves down. And worse than that, if the plan was that these AUVs were to move to their destinations concurrently, but we're not dispatching it that way, then the plan can be completely wrong. They would crash. The execution of the plan is no longer what the planner simulated when it solved the problem. So we can try to make the execution match more closely the execution trace that the planner expected by dispatching the actions at their estimated dispatch times. But if you've ever tried that, you'll know that it's completely impossible. The robot never reaches its destination waypoint on exactly the second that the planner thought it would. The real world's just not clean enough for that. And the domain model is always at least a little bit inaccurate. So for example, with the AUV domain, we had a navigate to this waypoint that we assume would take 10 seconds, but if there was a strong current coming from the top of the screen, the AUV is struggling to move through it at a slower pace. 10 seconds pass and it's only here. If we were executing these actions at their estimated dispatch times, we have a strange choice to make here. Do you execute this action immediately, or do you wait now until the previous one is complete? And this would be dependent on the kind of action. Some actions can be done concurrently, some can't, and it's completely unknown. So we could dispatch the actions while respecting the causal orderings between actions. First of all, we have to extract what are the causal orderings between actions, but this is a thing that's possible to do. If we know what the precondition of an action is, we can wait until those preconditions have been achieved before dispatching the action. And if that time is still before the estimated dispatch time, we could wait until the time at which we should dispatch that action. Unfortunately, that doesn't always work, especially when you require temporal coordination in your plan, if the temporal or time windows are involved. So for example, the current is still too strong from the top. As these AUVs move into position, the top AUV reaches its destination much earlier than the bottom AUV. But they're supposed to coordinate in order to inspect this structure here. One of the AUV has a light to shine on the structure, while the other AUV takes pictures at an angle to avoid backscatter. As this AUV hasn't reached its position yet, and this one's still illuminating, by the time this one starts to take pictures, this one's already finished illuminating and is moving off towards the next waypoint, and all the pictures that you end up with are completely dark. So what we need is a plan representation that includes more than just the estimated dispatch time of the actions. We'll need a formalism that's more expressive to be able to capture these things like causal constraints and temporal coordination. One of these related works that I showed before is about controllability. When you have a formalism that's a bit richer, you can start to define more properties about the plan. Controllability is one of them. In this case, strong controllability. So a strongly controllable plan is one in which, well, first of all, let's describe these diagrams. These are plans now, which have upper and lower bounds on the times the actions will take. For example, this is B1 is the beginning of action 1 and E1 the end of action 1 there. The planner has controllable and uncontrollable time points that the executive can choose when to start executing these actions, but it can't control when these actions will end. That's dependent upon the duration of the action, which is, we know some bounds on it, we've guessed some bounds on it, but we don't know for sure. We say that the plan is strongly controllable if before we even begin to execute, we can assign a time to all of the controllable time points, much like the estimated dispatch time that the planner has assigned, and then be guaranteed that as long as all of the action durations fall within the upper and lower bounds that we estimated, the plan will still succeed. All of the temporal coordination will kick off perfectly. In this case, this plan is strongly controllable. As long as you execute B1 and B2 pretty much at the same time, B2 has to be equal to or after B1, then this temporal constraint will also always be satisfied, because the duration of this is much shorter than the duration of this. However, this one is not strongly controllable, because no matter how early you execute B2 after B1, there's going to be the chance that B1 ends, action 1 ends before action 2 does. So strong controllability is a nice property to have. If you have that, executing your temporal plan becomes a lot easier. But it's not a very common property. This plan, for example, is not strongly controllable. So let's say this is a navigation action and then the inspection action as the AUV moves towards the structure and begins to take pictures. The navigation action has quite a high variance in its time that we estimated. It could take between 20 and 40 seconds. And we want to make sure to start the inspection no more than 10 seconds after the navigation completes. More than that and the AUV drifts too far. And then the inspection takes some amount of time. We can control the time at which we start the inspection, but there's no time at which we can decide that before we begin the navigation, and the plan will always succeed. The quickest the AUV will reach the structure is in 20 seconds, and in that case we can't start inspecting any later than 30 seconds into the plan. The slowest the AUV might be is 40 seconds, so we can't start in that case inspecting before 40 seconds. But these are disjoint intervals. So this is not a strongly controllable plan, but it's obviously an executable one. It's simple to execute. Move to the structure. When you reach the structure, start inspecting it. So we introduced this concept, dynamic controllability. And dynamic controllability is simply saying that the execution so far has led to a point at which the rest of the plan is still executable. You never have to make a choice about a time point in the future where your guess might invalidate the plan. So in this case, this one is dynamically controllable. By the time we have to decide when to dispatch B2, we now know what the real duration of this action was. And so we can make a guess about this, which will satisfy all of the temporal constraints. The summary of this is that in order to even reason about these kind of issues and to say that plans have these kinds of properties and then exploit these properties during execution, we need a plan representation that's more complex than a simple sequential ordering of actions with estimated dispatch times. We need a plan representation that can talk about the kinds of things controllable and uncontrollable durations of actions. Some actions you can choose how long they are. We need to be able to talk about causal orderings between the actions and the temporal constraints and coordination that's inside the plan. The planner knows about these constraints. They're modeled in the domain and the problem file, but they need to be made explicit in the plan itself for execution. This is why we have a separate,
For the previous ones, so far it kind of assumes that both agents execute independently. They have some idea of what the coordination needs to be. Is it possible to enforce synchronization practice, basically like periodic distributed computing? You execute up to this point, and then you have some sort of communication. You need to have some sort of communication event between different robots to make sure they're in the same spot, wherever that spot is.
So actually, so far when we have multiple robots, we've always used a single ROS master. So all of the robots are running on the same ROS system, communicating between each other all of the time.
Know where they are, can advance plans.
So in the situation where they can't communicate all of the time, it becomes a little more complex and they have to share information. And I've not actually explored that at all before. But there are even more plan execution issues there. We're going to be talking more about planning under uncertainty just in a few more slides, or maybe after the break. And then Luca will talk more about that as well in his part. But that's one of the ways in which you can see this limited form of communication between robots is as a form of uncertainty, where part of the state is unknown to you. All right. So this box, this plan dispatch box, which is sending PDDL messages to the lower level control, this is tightly coupled with the choice of plan representation. If you have something that's dispatching plans as if they were temporal plans, temporal graphs, but you're passing it a sequential list of actions, you're probably just wasting a lot of effort here. Whereas if you've got a temporal graph of actions and you're dispatching them sequentially, you're not going to get the behavior that you expect. However, the planner is also tightly coupled with the plan representation. If you want to generate a temporal plan with causal links between them, and you're using a classical PDDL1 planner, then you're not going to get that. So this is the reason this box is separated. It's to decouple the dispatch from the planner to allow you to perform some sort of conversion in here. And this allows you to mix and match planner executives with planners a little more freely. And there. So now we move on to the third set of issues in plan execution, which is uncertainty. And there are different kinds of uncertainty that can come up. So we've talked already a bit about temporal uncertainty, where the executive can't know in advance how long actions will take to complete. But this is only one kind. There's also the uncertainty upon the outcomes of actions that can fail, obviously, but also have multiple different outcomes, or even an infinite number of outcomes if it's continuous. You also have partially known environments, which is very common in robotics, where a robot will enter a room and doesn't know in advance if there are people in the room, how many, where they are, where the obstacles are. In this case, we still want to be able to plan, but it's very difficult to plan when the model is not completely known. So Dan has already introduced the idea of conditional planning. This is actually a screenshot from the web interface to ROSPlan. When you're using one of the conditional planners, you can see that the execution of the plan depends upon the outcomes of different sensing actions. I won't go too much in detail on just conditional planning alone, but rather try to combine them. What happens when you have a temporal domain and uncertainty? And when you're executing on board robots, these are the kinds of domains that you normally have. With all of these kinds of temporal constraints and uncertainties, the plan representations that you acquire, or the plan executive implementations that you want, can be very complex. So a couple of examples are plans are represented as GoLog programs or as PetriNet plans, which Luca will talk about in a minute. There's an example of a PetriNet plan, which he'll describe in much more detail. So with ROSPlan, we've integrated with the PetriNet planning library in order to, you remember that box that decouples the plan representation from the executive. We have an implementation of that node to just transform the plan into a PetriNet and pass it to the PNP ROS executive. Luca will talk about that in the next part. So here's a summary of the very simple plan execution that boots up when you start one of the demo files from ROSPlan. And an important point I'd like to make is that this box, I've called it plan dispatch because I don't believe that plan execution is just contained here, because this is tightly coupled to your choice of platform. You need these interface components to translate your symbolic PDDL actions into the goals for control, and it depends upon it needs to know which of these actions can be preempted and which ones can't be interrupted safely. It needs to change its implementation depending on whether or not these actions are able to return success or failure, and under what kind of context they can do so. It's also tightly coupled to the kind of state estimation. One of the assumptions we've made so far is that the state that we're building from the sensors is always correct and kind of complete enough. But it might not be, and if it isn't, that has to be handled as part of plan execution. It's obviously tightly coupled with the knowledge base because it's always calling those services to perform plan validation. And again, it will call the services of plan generation to regenerate the problem instance and call the planner and generate plans. And it does this for replanning, but also, as I'll talk about after the break, for being able to dispatch more than one plan at a time, or performing plan repair or plan merging. So really this plan dispatch box is coupled with everything else in the system, and you end up with this, like, you want a ROS system to be lovely and modular, and it turns out to be this kind of monstrous thing where everything is coupled together, and the whole thing is your plan executive. And that's not ideal. And you change any one of these parts, you change the way in which you store the state or generate the problem, or you change the representation you have of the plan, and the whole behavior of the robot can change, and the plans which will fail or succeed change. Okay. I'll start talking now about a few examples we have of using ROSPlan in our applications, in which we use more than just a very simple executive. In particular, dispatching more than one single plan. As Dan said previously, if we desire persistent autonomy, we're not just planning once and executing that plan. At least we'll need to be able to replan when the plan fails. But we can also have long-term goals and short-term goals, which we combine, as he talked about, in the strategic and tactical sense. I'll show you how we performed the strategic and tactical planning in ROSPlan. Okay, so one common simple scenario is planning for future situations which you can't predict. This is what I talked about before, where a robot's moving into a room, you don't know exactly what's there yet. Here we have an example that Dan showed using the simulator, where this AUV is to move between these different obstacles and begin inspecting them. But before it reaches the structure, it doesn't know exactly what the map will be. It has to build the map as it arrives. So it's impossible to plan for the whole thing in one go. Here is the overview of the strategic and tactical planning he talked about. First of all, we generated a tactical plan just by using the problem generation and planner and creating the plan representation as we would in the main system. And this is generating these temporal plans and getting the energy consumption and the duration of it. But these plans fed into the new domain file and problem generation of our strategic level. And this just works exactly as we talked before. This system is generating a strategic plan and beginning to execute it, sending to control these high-level navigation actions to move between the seabed manifolds, and then also sending actions which are the complete mission actions, sending this kind of this plan. However, upon dispatching these complete mission actions, the control for that kind of action is another planning system, another set of ROSPlan nodes wrapped inside one of these ActionLib servers, as if it were just an action. And this reports the success or failure of the complete action mission back to this plan dispatch. But within the tactical mission, the whole process of problem generation, planning, parsing, dispatch, and replanning, and validating against the knowledge base is still being performed. We then wanted to generalize this concept. So this works well with two layers, but in the case we have of an unknown environment, we found that it could be quite useful to be able to extend this to many different layers. So in this example, we have a robot that needs to inspect and uniquely identify some objects in a room. So it moves into a room, first of all, without knowing where any of the objects are. Then once it's identified where the objects are, it generates a set of view cones around each object from which it will start to build a 3D point cloud. After each view cone has been visited, it makes an attempt to identify the object. This identify action has actually 3 outcomes. It can succeed, at which point you don't want to visit the rest of the view cones. You want to stop immediately and move on to the next object. It can fail, and so you must move to the next view cone if there's any left. Or it can fail, but the number of candidate objects is now small enough that the control for inspection can generate a unique view cone which will discriminate between those candidates. And in that case, you don't want to visit the rest of the view cones you already have. You actually want to replan using the new view cone that's just been generated. So this is the kind of conditional plan that was generated in this case. And this observe classifiable upon attempt is a strategic action. And this strategic action corresponds to moving around and observing the object from different view cones. The outcome of this could be success, in which case you want to finish immediately, or it could be failure. But in this case, the failure might return new view cones, these discriminatory view cones from which to view the object, in which case when you move on to the next observe classifiable upon attempt action, you can use these in the new problem generation. You don't have to do the planning until you reach that portion of the environment. And this is important because these plans might not be trivial. The identifying controller, the part that performs the inspection, doesn't really understand the rest of the room. It doesn't understand the navigation or the object collision. It just says this is the angle from which and distance from which you should view the object. This might mean that you have to push other objects out of the way in order to be able to make this inspection, or even pick up the object and move it away from some walls to some clear space before you can perform the action. So it's definitely a place where you need to do some planning, but you can't do the planning until you reach that point. This is the system that's built for that. In this case, each one of these hierarchical levels of tidying the room, examining the area, classifying the object, and so on, has its own problem generation and executive. But these executives are sometimes dispatching actions which cause a new problem to be generated and a new executive to start beneath, which will then return success or failure to its parent. One thing to know is that we were fortunate enough to be able to use the same plan representation and planner for every level of our hierarchical planning. In this case, we used a contingent planner and we had no temporal constraints. Here is the platform. I've expanded now this single-boxed platform to show that there are all these interfaces that have to be written in order to convert the symbolic to the concrete ground truth, as I showed before. Although these are all available online as well. We have a growing library of these. Okay, so one thing to note is that none of these boxes are new. We had all of the code available already, and all of the code on the board, the robot, to perform the individual actions was already written. We just had to link them all together. But that itself is not a trivial step, and just by changing the way in which these different components called other components, we've completely changed the behavior of the system, and are able, in fact, to solve problems that we couldn't possibly solve using the very simple dispatch I showed earlier. So that's 5 minutes to break. Should we pause there? Yeah. Okay. All right. I'm going to just finish off my part now and pass over to Luca. So I was just going through some case studies before the coffee break on how we set up ROSPlan to perform the strategic and tactical planning, and then generalize that into a kind of recursive hierarchical planning. I'm going to do the same thing now for the opportunistic planning that Dan talked about in the first part. and then about our integration with the PetriNet planning, and then pass over to Luca. So for the opportunistic planning, just to remind you, we were generating new plans on the fly when we came across opportunities, or when new goals were added by a user, or various other things. To do this, we had a very simple algorithm which built a window of free time. Oh yeah, thanks. Okay, now I'm on a timer though. No, it's fine, I forgot. The free time window is built up because we took a very conservative estimate of the durations of actions. We assumed that the actions would take in the 95th percentile of the variable time that they normally do. So in reality, when we executed the plan, this free time window built up, and we were able to insert opportunistic plans in the middle. And as Dan said, this approach was recursive. We were able to exploit one opportunity while exploiting another opportunity, and then eventually get back to the main plan. This was the setup we had. We have one new box here which I haven't mentioned before. I'll mention in a second. But really, if you ignore this box on the right hand side, what you have is just the very basic ROSPlan setup, where we are planning, replanning, and interfacing with this AUV using the ROSPlan to COLA 2 interface. COLA 2 is just a control architecture for underwater vehicles. What was new was when an opportunity was spotted, this second problem generation and plan merging component was called. Dan will be talking more about planning for opportunities in a journal paper presentation later this week, and he'll describe the approach we took to this. But just briefly about plan merging, there are of course many solutions to this this problem already. This is work from Lenka Madrova, who's here somewhere at the conference, where she shows that sequencing plans one after the other is less efficient than merging them, while unifying them, that is, just to take all of the goals from both problems and creating a single plan to achieve them together. Although this can be as efficient, or even more efficient, than merging the plans with some plan merging algorithm, for our problems it was impossible, because they were too complex, they were too long horizon, and our AUV only had 10 seconds to plan before it would drift away. Right, now I'll talk about our integration with PetriNet planning. So, one thing we were assuming is that our state estimation is updating the state with the information that we actually need to be able to tell whether or not the plan is valid. This might not be the case. This zombie behavior I talked about at the start still crops up from time to time. And this part of the system is part that PetriNet planning will replace. It performs its own state estimation internally that doesn't need to feed back into the PDDL model. And importantly, all of the state estimation there that's performed is the state estimation required to be able to validate the current actions in the plan. Similarly, these components which translated the symbolic PDDL into the low-level control will also be replaced by the ROSPNP library. And finally, this node here, which determines which actions should be dispatched to the controllers, is replaced. So these three parts aren't required when using ROSPNP. Instead, we have a system that looks like this, where ROSPlan components are really just used to generate the PDDL problem file, pass it to a planner, and generate an initial plan. In this case, a conditional plan, one of the branching plans we looked at before. Then ROSPNP takes care of the rest. This is on its side PetriNet plan here, and integrates with the platform itself. This box is has its own complex description, which Luca will cover in the next part. Okay. As a final slide, I'd just like to point out that the documentation and source code for ROSPlan is available on this website, as well as the slides for this talk, and the virtual box that Luca has will be there soon too. Okay, that will conclude my part.
Okay, so in this third part we'll talk more about execution, and in particular by using the PetriNet plans formalism. It is a formalism that we use in many applications for describing plans for robots, and also for other domains. So PetriNet plans is a formalism for plan representation, so it's not a planner. And, but this formalism has been designed in such a way of using the definition of plans that are usually considered in the planning domain. So in other words, this planning formalism is able to represent explicitly actions and conditions that are typically mentioned in the domain of a planning system. So in this way we can match the theoretical part of the planning system, in which we describe the actions in terms of preconditions, effects, and all the elements that we have seen that we can do this in PDDL, with the execution part. And so this is contained in a library that is available together with ROSPlan, and the library contains the PNP execution engine that I will describe, and some tools to generate PNP, not to generate plans, but to generate PNPs, as I will describe. And so this is a standalone library that can be used in many applications. We have bridges for us, of course, that is the main topic of this tutorial, but we also have bridges for other environments. For example, we recently are working on a pepper robot, and so we implemented a bridge for the Iocchi environment. So why we want to propose to use PetriNet plans for representing plans in robotics? Well, of course, PetriNets are very expressive formalism, and with PetriNets you can express in a compact way all the behaviors that you really need to run on your robots. So PetriNets are exponentially more compact of transition graphs, for example, and this means that they are very powerful in terms of representation of complex, very complex activities. And this means that for sure PetriNets can represent probably all the plans that are considered in the planning community: linear plans, contingent plans, or plans with loops, policies, and maybe also some kinds of temporal plans. So we can say that PNP can be used as a general plan execution framework. So you can imagine that any plan that is generated by any system can be represented as a PetriNet plan in particular, and then you can execute this PNP. And this is what we want to show in this part of the tutorial, and in particular to understand how the PNP engine is working together with a planning system, the ROSPlan in this case, and with the ROS system that will be used to control the robot. And to do this combination, we need to translate some structures, in particular the plans that are the output of typical planners in PNP. And so the PNP Gen library is a library with some tools to generate PNP from many different plan formats. So this is integrated with the ROSPlan, so any output of the ROSPlan planners will be transformed in a PNP, but it also includes other plan formats support, like HATP or MDP policies. Of course, this is extendable. So the main idea is then that in order to execute the actual plan on the robot, we know that ROS is a very common framework for robotics application. So the PNP ROS is the bridge that actually allows to execute the plans on the robot. So this is an overview of the system, and what we want to highlight is what is the part of the system that is domain independent with respect to what is domain dependent and must be provided by the user. So the goal is to clearly separate what is domain independent. It means there's a library that you can download and use it as it is, maybe even as a black box, because you don't have to put your hands into it. And what is, of course, domain independent? Domain dependent means that you have to write the specification of your actual system. So the main goal is that all this blue box that you see here must be domain independent. This means that you can use this as a black box, and you have to provide some information like the domain, the goal, or the specification of the word, and I will talk about execution rules, and then you will see your robot doing what you specified over there, without writing anything, any line of code into this blue box. Of course, this is very optimistic plan, because we will see that sometime we have to use some tricks in the, for example, in the execution framework in order to make this system really work on the robot. As we have seen in the previous part of the presentation, the output of a planner usually is not robust enough for being executed directly on the robot, because there are many uncertainties and there are inaccuracies and so on. So what we added in this system is a robustification phase that transforms a plan into another plan. This other plan is more robust with respect to the plan generated by the planner system. And I will describe how this is done. And at the end, what we have is this PNP that is a complex behavior, that represents a complex behavior. So not only the planner that is generated by the planner, but also what is generated by this phase. Now, once we have this PNP encloses all the information that we want to execute on the robot, including all the sensing. We have seen in other models of an executor that you have to maybe implement a state estimation functionality on your system. This means that you have to decide, for example, which processing units you have to run on the robot at which time, or maybe you try to run everything at every time, hoping that everything will go well. And this is very complex. In the end, what happens is that the overall behavior of the robot depends, of course, not only on the plan, but also on all the tricks that you have encoded in the executor module. While here, what we try to avoid to put any trick that is hidden in some piece of code, but we want that all the tricks that you want to, or all the hacks that you want to put on the robot in order to make it work are explicitly defined in such a way that you can monitor the execution, because the PNP has a standard operational semantics, so you can actually monitor what's going on. So the idea is that only this PNP will be executed without any other piece of code that is hidden. And so if there is a failure or there is something that doesn't work, you can look at the PNP and check what's the problem. So this is integrated with ROSPlan in a way in which we saw before. So we keep the part of ROSPlan that manages the knowledge base and the problem generation, the planner, and the plan parser. But then here we replace something that in ROSPlan was done with some specific techniques with a more general framework that is the one of PNP. So with the goal of having that also this part in this system will be completely domain independent. It will not require you to put your hands in this component at all. So the outline of this part will be, I will briefly say a few words about Petri nets, and then we'll focus on Petri net plans, that is sub-language of Petri nets, and then I will go quickly through the execution rules, show how all these are integrated in PNP ROS, and then at the end I will show you a demo of all the system working. So, very simple, Petri net is a biparted graph in which you have places and transitions, and each place is connected to a transition, each transition is connected to a place. And the concept of a Petri net is that places can be marked with the markers, so the state of a Petri net is given by the presence of markers in all the places. Okay? So a Petri net is a complex structure of these items that are connected to each other, and the state is characterized by the places that have tokens in it. And the evolution of a Petri net is based on the firing rule. So a transition is enabled when there is a place, when there is a token in the place before them. And the transitions are also usually labeled with conditions that, for example, in PNP, they are conditions that are validated in the knowledge base of the robot. And when a transition is enabled and the condition is true, then the transition can fire. And firing the transition means that the token will move from this place to the place after the transition. Okay, that's the execution module of Petri net. Of course, depending on the situation that the Petri net that you are that is evolving, you may have situations like this in which if both these conditions are true and both the transition are enabled, they can both fire, and in this case you will have that this token will duplicate and will continue on all the places like this. Okay, so this is just very quickly about what is Petri nets. So what are Petri net plans? So it's a representation formalism to represent plans with Petri net that introduces some constraints about how the Petri net can be formed. So a Petri net plan is a Petri net, but it is not true that any Petri net is a Petri net plan. Okay? So the idea is to not accept any possible Petri net, because then it becomes difficult to prove some properties and also to run algorithms there. But have that the Petri net plan is a proper combination of these elements. There are two possible actions that we can define in Petri net, in PNP, that are ordinary actions and sensing actions, and there are a set of few operators that you can use to combine the actions among them. So a Petri net plan is whatever you obtain by applying these operators to actions, so you cannot do anything else. So ordinary actions are just actions that represent a time durative execution of an action. So places are representing the fact that the system is in a given state. Actually, it's a partial state because the state is given by all the tokens in all the places. But if you consider only, for example, this part of the PNP, we have that the initial place means that the action is not yet started. The start transition is the transition that happens when an action starts. The execution place is a place that means that the action is under execution. The end transition is the event that happens when the action terminates. And this, the last place, is the state in which the action just terminated. Okay? So in this way we represent an action that can start at some point, it will remain in the exact state for a while, and then it will end after a while. Well, a sensing action is similar, but since we are sensing a property. This is a case of binary sensing, but of course can be extended to also non-binary terms. Then you are the execution action. At some point, you have a branch, because the flow of execution will depend on the actual value of the sensing. And here we have these two conditions, the T and TEF. And these conditions, we assume that are mutually exclusive. Okay, they must be mutually exclusive, because otherwise you may have that both the transition will fire and then you will execute both the branches, which is not what we want. So in a sensing action with mutually exclusive transitions, what is the effect is that you execute the sensing action. At some point, one of the conditions will become true, and then only that one will fire. And so this means that the token will pass from the execution place to only one of the final state. And this allows to execute branches. So this means that the action will be executed. If the property is true, we will go up. If it's false, we will go down, and we continue only on this. And if as I said before, if the transitions are all mutually exclusive, there is no possibility that all the branches will be executed. So these are the two actions that we can define PNP, and then we can use some operators. So very simple, the sequence operator just join the end place of one action with the init place of another action. So you take these two places, you merge them, and you have a chain of two actions, like what you see in the upper part of this slide. Then you have the interrupt operator that is applied to the execution action of an action, the execution place of an action. It controls a condition, and if the condition is true during the execution of an action, then you have a transition to exit this action. This is useful to denote situation in which you want the action to be interrupted because some event occurred. And then in order to deal with concurrency, we have the fork and join operators. So the fork operator is just operator that forks one token. So when this transition is true, one token becomes two tokens. And then this means that you can execute two threads of execution in parallel. And of course, the join action do the opposite and will join different flows of execution. So examples of interrupt, very often in robotics there may be situations in which when a condition or some event happens during the execution of the action, I have to do something else, because this means that the action is not good anymore. For example, a robot playing soccer that is moving to the ball to get to the ball to do some soccer action. But if during the execution of the action the ball is not visible anymore, or the ball is stolen by an opponent player, then it cannot continue this action, but it has to do something else. So this is an example in which what we say is that if during go to ball there is the event stolen ball happens, then the robot will go back to defend. Okay, and this is an example of fork and join. We want to execute two actions in parallel. One is going to the ball, and the other one is track the ball with the head. So imagine you have a soccer robot with, for example, a humanoid robot, and while you control a part of the robot, for example, the legs, to walk towards the ball, you want at the same time in parallel to control the head, for example, to track the ball. And you can easily do it by a fork and join operator. This means that these two actions will be executed in parallel, because you will have the tokens in the execution places of both the actions, and then when these two actions terminates, then you can proceed with the plan. So some examples of how you can combine these things to form complex plan. Of course, the sequence can be also applied backward, so you can implement loops very easily. So this is a loop in which you do these actions forever. And of course, combining, this is another example in which you have a loop. Inside the loop, you have some parallel actions. So this means that you are doing, for example, init, then there is a fork. These actions are executed in parallel, and then you join, you execute another action. This goes back again forever. This is an example of a while loop. If you combine sequence with sensing action, you have this situation. So this is a loop that says that until this condition is true, then you will execute this this task. For example, here it says that until there is an obstacle in front of the robot, then the robot waves. I don't know, whatever you want. And then as soon as this condition becomes false, then you exit the loop and you do something else. Okay, so you can represent very complex tasks. And of course, you can combine everything with interrupts. So this is similar as before, but now we have an interrupt. So this means that we add something that if we detect an obstacle during this action go to pause, then we do something else. Okay, so even if we have just a few elements, 2 actions and 4 operators, we can combine all these elements in many complex ways and form plans that are very complex. We also have some operators for multi-robot plan execution, but will not describe this in details. But of course, you can imagine that some of the actions are referring to different agents, and we have defined several multi-agent synchronization operators. Okay, so once we have this complex PNP that can be formed in this way, we have to execute this PNP. What is the meaning of executing a PNP? You just want to evolve the Petri net that is underlying the PNP according to the Petri net semantics and according to the information that we have in the knowledge base. So very simple, what the execution algorithm is just considering the initial marking. So the initial marking is usually, for example, in this case, you see that we usually start with a token in an initial place like this, and then this token will move during the execution. So we start from an initial marking, and we look for a goal marking, if any. So this process will be repeated until we reach a goal marking. And what we do is very simple, just apply the firing rule. So we check all the transitions that are enabled, and for all the transition enabled, we check if the conditions are true, and for each transition that is enabled, so that means that there is a token just before it, and for which the condition is true, and this is done by just querying the knowledge base, then we activate the transition. Activating the transition means that we fire the transition. That means that we move the places from the tokens from the places to the input places to the output places. But then we also do, so this is a standard execution of Petri nets. What we just add is that the handling of some special transitions. And the special transitions are the transition that starts, ends, or interrupts an action. Okay? So whenever there is a transition, the PNP executor will just check if the transition is a start transition or an end transition or an interrupt transition, and it will send a proper signal to the action to be started, ended, or interrupted. Okay? So very simple, but also very effective, very clear. You usually understand what's going on. And what we can also prove is that this execution algorithm is correct with respect to the operational semantics of the Petri nets and to the robots local knowledge. So this means that when you execute the PNP, the execution on the robot is correct with respect to what you write in the PNP and what is the current information of the robot in the knowledge base. And of course, this is important to have some correctness result. Okay, some other features of PNP that each action can be a PNP subplan. So this means that we can organize this PNP in a hierarchical form. We have defined a way of using variables, but I will skip this part because I don't want to enter too much into the details. But what is important is that even with this nice mechanism of PNP, so either what we did before looking at the planning system was to write these plans manually. Because, of course, the structure of the plan is very complex, and there is no planner that is able to generate a PNP like this. So what we have done in the first years is that the plans were written manually with a graphical editor, but still manually by people. And well, you can reach good results up to a complexity level. But if you go over this complexity level, it's very difficult to manage a big PNP by hand, because it's very difficult to write a correct PNP for your problem. So in order to, but on the other hand, if you use a planning system, you can just generate very simple plans, maybe linear plans or conditional plans, and they are not enough to be executed on the robot, because there is something that is missing. For example, how to generate interrupts, how to say the robot that he has to do something in case of something goes wrong is very difficult. So what we add this level of execution rules, there is a way of formally define what is the behavior of the controller when there is something unexpected. So the main idea is that, if you go back to this slide, is that the plan that is generated by the planner is the optimistic plan that will work when everything will go well. So it means that, for example, users will act according to what the plan is defined, that the model of the planner is correct with the environment, nothing strange happens. But whenever there is some inconvenience in the execution of the plan, this plan will fail, and maybe even worse, the robot does not even know that the plan is failing. So what we do is to add these execution rules that are then merged in the PNP, and these execution rules are able to specify what is the behavior of the controller, that will be the PNP, when something goes wrong. And the feature of these execution rules that it can use some variables that are in the domain, in the planning domain, but it can also use variables that are not in the planning domain. This is very useful because, for example, if you consider a situation in which you want to add a new variable to control the behavior of the robot, and if you are forced to add these new variables in the planning domain, then you will increase the complexity of generating the plan. And since all these variables that may determine some inconvenience of the robot may be many, this will exponentially increase the complexity of the plan generation procedure. So for example, I want to do something when the ball is stolen, or when the battery of the robot is low, or when there is a person jumping in front of the robot. There are many variables that can determine some variation of the plan. If I put all these variables in the planning domain, this becomes not possible to generate plans efficiently. So the idea is that here we can put variables that will not affect the domain, the planning domain, but will affect the plan. So they will affect the behavior of the robot without affecting the complexity of generating the plan. And we will do this in such a way that everything will be into the PNP, and so we can fully model and understand what the robot is doing, because also these execution rules, the way in which the execution controller must act, will at the end be here. So, and we want to avoid to use C++ code for this task, but we want to use high-level formalism, a declarative language to say these rules. So these rules are rules like this. For example, we have rules that says that if something happens during the execution of the action, then you have to do this recovery procedure. Or you can have other kinds of rules. So these rules are directly mapped in some modification of the PNP. For example, a rule like this means that I will put an interrupt with the condition person here and close to target on the action go to, and if this condition is true during the execution of the action, then, for example, in this case, I will skip the action and continue with the next action. Okay? So the idea is to provide at a declarative level ways of modifying the PNP to add some features that are important during the execution of the of the plan. And so nothing else. So only what is written here will affect the control of the robot. Okay, so in order to implement all of this, we have so the PNP engine is a library, but we want to implement this on top of a robotic application. So we implemented this bridge between PNP and ROS that is using the action lib protocol that was mentioned before. So this is a sketch of the situation. We have a plan that is generated in some way with ROSPlan or with the system that we are describing, or you write this plan manually, whatever you want. And then you have this part that is the domain-independent library. So here you don't have to write any line of code. You can use this as a black box. And what you have to write is this part that consists in the actions and the conditions that are specific of the plan. So the plan here will mention some actions and some conditions, and of course you have to provide the implementation of these actions, these conditions for the robot. And I will show you how to link this to all the rest of the system by just adding, in this case we have a C++ implementation, so this my PNP action server class that will be a subclass of the PNP action server class that is provided in the library. So here you have all the complexity of managing the plan that is domain independent. So you don't have to do anything. There is the PNP engine library, a service client, an action client that connects to the action server and the PNP services. All these components are provided in the library and they are domain independent. They are ready to communicate with what you provide. I will show some of them during the demo later. So what you need to use PNP ROS? Well, you need a plan, or you need a planning domain and a planning system that generates a plan. And then you have to implement the actions on your robot and the conditions, of course. And you have to write this PNP action server. Just to give you an idea, the PNP action server is this class that you find implemented in the PNP, in the ROS PNP library. That okay, there are some functions. What is important is the action execution thread and the eval condition. So you need to provide an implementation, an actual implementation of how the actions are executed and how the conditions are evaluated. This is done by registering the actions through a specific function. And so the minimal action server that you have to write to use the PNP ROS library should contain, so should be your class that derives the PNP action server class that is in the library. And here you have to provide what is the link between the names of the actions that are in the PNP and the functions that implements this action. So in PNP you have just strings representing actions. In it, go to kitchen, go to ball, kick, and so on. And you have to provide a link between this string and the function that will implement this action. And this is done very simple with this example. For example, in the Python version of the action server, this is not even needed, because in Python you can evaluate the strings as a functions. And then in terms of conditions, you have to set the value of conditions that are done by some processing modules on your robot. And this is done very simply, again, by using a standard ROS functions. In particular, here we are using topics to send asynchronous events. So whenever a routine detects something that is relevant for the planner, you can write the name of this condition on a topic. Or if it's a synchronous event or a synchronous processing, something that is computed at every cycle, you can just write the value on a parameter, on a ROS parameter. So this means that in this way, you are able to match the names of the actions with functions that will be executed. And you are able to match some computation about sensing with strings that will activate the conditions on the PNP. Okay, so what I will show you now is how all these things have been integrated in a demo that is done on a virtual machine in which everything is installed. And this virtual machine will be available on the tutorial website very soon. Actually, it's not yet available because I keep changing and improving. So if you downloaded this virtual machine, this is a virtual machine with Ubuntu 14.04 and ROS Indigo and the ROSPlan and PNP and all the actions implemented. So you can play with the full system. So you can write your domain and see what happens in the simulator. This is a simulator. We use a stage simulator because it's compatible with a virtual machine. Of course, you can use other simulators, but they will not run in a virtual machine. This is quite a small virtual machine. It does not require too much computational power. Of course, if you want to use other simulators or the real robot, probably you need to install everything on the real machine. But in order to play with the ROSPlan and PNP, this is nice. And also, we choose tasks and environments not in a realistic way. So this is the map of an apartment in Peccioli, in which we did a robotics competition in the framework of the RoboCup at Home and the European Robotics League. And this is actual representation, a simulation of tasks that are done during this competition. So this is exactly the map of the environment, and this simulated robot simulates this robot that is doing some tasks in this environment. And the tasks that we have chosen here, they are not invented by ourselves, but we try to really do some exercise of using planning for tasks that we are interested in. And so we get inspiration by the RoboCup at Home domain. RoboCup at Home is a competition in which robots have to execute tasks for assisting people in an environment, for example at home. And we took a couple of problems from the RoboCup at Home rulebook, and we defined the domain and the plans from these problems. And actually we are using this framework for our team that will compete in the RoboCup at Home in 1 month from now, not with with this robot, with the Pepper robot. So we hope that we can show that this technology is useful to solve systems, to solve problems in real systems. Okay, any questions so far? So, what is very good of a virtual machine is that we can freeze everything and make to the point that I just have to click the start button to run the demo. So hopefully there will be no demo effect. Well, we never know because there are some real-time issues that happens also in this kind of demo, but of course it's much easier than doing a demo with a real robot. So here you have all the environment that you will find in the virtual machine. And just to hide a little bit of the complexity of ROS, Michael was mentioning that to start a ROS environment, we have to run many launch files, and this is actually the case. Here what I've done is very simple interface in which you can have some choices to start a demonstration. So here you can choose which map, which kind of robot, some parameters of the system, localization system, navigation, the kind of demo, and so on. And so at the end, when you do all these choices, and you can click start. By the way, everything is described in these README files that you will find on the desktop. And so when you start, everything happens. So what you will see now is the launch of many launch files that are useful to run this application. And there are many nodes. Now we are running all the ROSPlan nodes, the PNP nodes, and all the nodes that are necessary to run the actions and the conditions of the plans that we have generated. So usually you will see many windows like this. And nothing happens. So here you have this window is about the ROSPlan system that is ready to receive the domain and the planning problem. And this other window up there is the PNP ROS that is ready to receive a PNP plan. And nothing happens until we say to the robot to do something. So here is the example of the domain, the RoboCapTom domain that contains, so it's a PDDL, I don't know, which version is this? 2.2? Okay, whatever, it's this one. Because in this particular case, we are using the contingent FF planner. But of course, you can use different planners and different domain specifications. So this is a domain, I call it the RoboCapTom domain, in which we have representation of the environment and some actions that the robot can do. So the robot can move in the environment, can interact with people. In this cocktail party task, the robot has to go to a person, ask if the person wants some drink, then go to the kitchen, fetch the drink, and bring it back to the person. The navigation task is a task in which the robot has to do a navigation in the environment. And of course, so the idea is that this domain includes all the possible actions that can be done in the entire competition. And then we have different problems that generates the plan for different tasks. So here, okay, I will not go into the details of all these actions. And, sorry, let me give some power. Yeah, what is strange is that most of computation time at this moment is taken by the stage simulator that is recasting the laser scans and is computing the position of the robot, even if the robot is not moving at all. Okay, so this we will run this domain, this problem, in which we specify that there will be a person in the living room. The living room is this part, and but the robot does not know if it will be able to detect the person or not, because detecting a person is not easy. And so this means that when the robot will reach the living room, it will look for a person, but it may be the case that this person is not found. So in that case, the rules allow two behaviors. If the robot is able to detect the person, then the robot should approach the person and say something. Otherwise, the robot can call the person. So if the robot is not able to detect the person, it can say, "Hey person, please come here." And so the person will approach the robot. So depending on this situation, there will be this branch in the conditional plan. And then the robot will ask which drink do you want, and of course it doesn't know what will be the reply of the human. We cannot assume anything about user needs. And depending on the answer, the robot will go to the fridge. Of course, we will not simulate any grasping of drinks from the fridge. This will be very difficult part. Here, the action grab something will always terminate successfully, which is good. Of course, it's not the case in the real world. And then the robot will go back and find this person. So, in order to run everything, we just send a call to the planning system that generates the plan and is executing the plan. And then I will show you the plan later. Now the execution of the plan is that the robot is going to the living room, and now is looking for a person. By the way, there are no people in the living room at this moment. Well, people are these boxes. So now the robot is say to the person, "Come here," and is waiting for someone to appear. And someone appears when you put something in front of the robot. There is a simulated laser that detects an obstacle in front of the robot. And now the robot is asking, which drink do you want? In order to specify which drink we want, well, of course, on a real robot, we have some interface like speech or a touch screen. Here, we just send a condition through a ROS topic. So I can say, I want a Coke, by sending a condition whose name is drink Coke. But we can choose any other drink. Anyway, we will not get any drink at all. So now the robot knows which drink the user wants, and it will go to the kitchen to grab the drink. Of course, the grab the drink action is a fake action, just print success. And after a while, it will go back to give the drink to the user. Here we assume that the robot will say, "This is your drink, please," or if there is a manipulator, it will hand over the drink. Now it's waiting for a signal for the human, and the human will, for example, say thank you, or will say something, or will click an interface. This is simulated with the condition done. That means that the user has taken the drink, and now the robot will exit to the apartment. So this is the plan that is generated by the planning system. Very simple. There is so enter, go to the living room, look for a person, sense. So this is a sensing action, if the person is detected or not. If the person is detected, then the robot will approach the person. Otherwise, it will say, "Come here." Okay, so this is the part in which there is the conditional branch. Then the robot will wait for a person to come here, then it will ask which drink. And this is, here we are using the variables in PNP. So the answer of the user will be stored in this variable x that will be used later. So this is a kind of sensing action, but with the sensing is included into a variable. So the value of the answer of the user is stored in this variable x, and this is used later. For example, in the action grab drink, I got that this value x will be instantiated with the answer of the user. So the robot will know which drink to grab when at the fridge. Then it go back to the living room, and it will tell to the user to take the drink. It will wait for the user to say, okay, I'm done, and then it will go back to the entrance and then exit. Okay. Now, this plan seems very nice and seems to work, but I can introduce, or maybe you have some ideas of something that may happen even in the simulator. You can introduce many situations in which the plan will fail. Do you have any suggestion how to make this plan fail? No, you know so many.
We can ask something to drink that we don't have.
Okay, but this is not a failure in the plan, I would say. I mean, at this moment, for example, we are not modeling which drinks are. Okay.
Can I?
Yeah, sure. I was joking.
Can you get the person to wander off while it's fetching the drink?
Sorry?
Can you get the person to leave the house while the robot is fetching the drink?
Yeah, so you can have some situations like this. But let me start with one that is very simple. It's not even a failure, but it's a behavior that probably is not nice. So I will start again the plan. Now it's generating the same plan, and we'll start again the plan. Now the person is already here in the location, so there is no need for the robot to look for the person, right? But actually we'll do it, because in the plan there is nothing that says if the person is already there, then you can skip, for example, all this part. So what you will see that the robot is looking for the person, and this look for the person is just implemented by rotating here. And now it's asking which drink and so on. But you see that this behavior, of course, is weird, or is one of the zombie behavior, because what happens is that you are looking for a person while there is a person over there. So imagine a robot comes to you and you want to order your drink, and the robot starts to do like this, and it prevents you to interact. So how can we deal with this situation? Well, of course, we can change the domain. We can try to put something like this on the domain knowledge. But this is just a small example of many that can happen. If we change the domain model for every of these problems, it will be very, very complicated. So what we can do is to use the execution rules, as I said before. So here, what we can say is that, for example, if there is a person, while I'm moving to this person, or while I'm doing the look for action, then there is no need of continuing this action. Okay? So I can add these execution rules here. Now they were commented before, so that they were not applied in the previous plan. Now, when I will restart the plan, these rules will be considered and integrated into the PNP. And we will see a behavior that in this situation, when the robot is in doing the action go to, there is the action to move to the living room, and this condition person here and close to target is true, so it means that the robot is able to detect a person, it's close to the target when he has to arrive, then there is no need of continuing the action go to, and this action can be skipped. skip action puts an interrupt on the go-to action with the condition end person near close to target, and this interrupt will jump at the end of the action. So the action will be interrupted, and we continue with the next action in the plan. And by the way, the next action is look for, but also in this case we can skip look for, because if you have a person in front of the robot, there is no need of looking for the person. So by adding these two actions, these two execution rules, both the go-to action and the look for will be skipped. This means that the robot, as soon as it sees a person, it will start the phase of ordering something. So we can see this behavior. By the way, when I start a new plan, whatever is the status of the execution of the old one, the robot will start again. So now the robot will start again the new plan. And now the new plan contains the effects of these two execution rules. So what we will see is that, hopefully, that was a misbehavior, that actually the execution has been suspended, but that was turning a little bit, so it's not facing the human. This is because there is no action at this moment that in the plan to face a person. So the robot is just arriving, and when it detects a person, it stops. But it's now starting the interaction without having executed the other code. So we can try again. Maybe we have to do a different. Then I'll come to your example. Okay, so you see that this behavior is reduced and not completely removed. Okay, now another interesting aspect is the following. Now let's assume that the person goes away, and the robot is waiting for an answer, because it's in a part of the plan in which it's waiting for an answer from a person, but this answer will never come because the person is not there anymore. So again, this is a situation in which what we can do is to make the plan more robust to this situation by, for example, adding another execution rule like this that says that if there is no person during an answer action, then you cannot just stay there forever. You have to do something else. For example, in this case, the recovery procedure is just to go to the exit and fail the plan. But of course, you can have a recovery procedure to go somewhere else to find another person. So with this rule that is very similar to what you say, you may have this execution which the robot goes to the living room, is looking for a person, the person will show up at some point, and now it is asking for a drink, but the person will go away. Let's see, I think this is sorry, let me restart, because this behavior of rotating is not well, what is nice of this procedure is that you can debug the plan and finding ways in which it fails. For example, this behavior of rotating is not good, and you can incrementally adjust the plan. So now there is a person. Sorry, you see that the demo effect acts also in simulated environment.
You haven't saved the execution rules file.
Oh. Yes, that's the problem. So of course you have to save your files before. I have to put this in the notes. Thank you. Okay, so a person appears. Now the robot is asking something. Now the person goes away without answering, and the robot will execute the recovery plan. So you said that the person is not there anymore. Let's see. Yeah, because here there is no action.
To handle the...
Yeah, there is no action to handle. Maybe we can do with the say, yes. So we can add that if not person here doing say, what do you want to do? You can say, where are you? Well, of course, now we don't have the implementation of this say, but this is just, and then restart the action. So the behavior would be that if there is no person when the robot is delivering the drink, then the robot will say, hey, where are you? And then it will restart the action. But then what happens is that this will loop. And the robot will keep saying, where are you, where are you, where are you, where are you, until someone will appear. So maybe you want to do something better. Of course, here you can add specific actions that you didn't imagine. Anyway, we can try this one, save. And here what will happen is that there will be this loop, where are you, until a person will go back in front. But it is anyway better than not say anything, because a robot that just arrives there and doesn't say anything will not activate any behavior from the user. So here we have to tell the robot that we want to drink something. So while the robot is executing the plan, with this tool, I think what you can do is very nice, is to play a little bit with the domain. Of course, now we are playing only with the execution rules, but you can play with the actions, you can play with the goals of the planning task, and you can see how the plan is generated and executed. And what is nice, the exercise that I do is to find what are all the possible ways in which the plan can fail. This is the exercise that you have to do. So you said now the robot is saying, where are you? You can see this written in the screen over there, until the person will show up in front of the robot. Now it says, this is your drink. And then once you send the done condition, the robot will go away. Okay, so I can show you the plan that is generated. And this is actually a very simple plan. It's just a plan in which here you have the branch. So you remember the plan that is generated by Conditional Planner. You do some actions at the beginning, then here you have the branch. And from this branch you start doing something when the person is detected and something when it's not detected. Actually, even if this part of the plan is the same, the planner does not generate I mean, the plan just generates trees and not DAGs, and so this means that these parts will be duplicated. Of course, there is no problem for the PNP. And here you don't see, you see some problems in how this plan is printed, because some of the text is overlapping. Also, it's not nice to draw a nice PNP, so the program that is generated this PNP is just trying to guess where to put the places, but it's not doing a good job on it. Of course, from the execution point of view, there is absolutely no problem in where you place this in the visual interface. So the PNP executor is not affected by the layout in which you show the PNP. But of course, for us to understand what's going on, we sometimes need to change the layout in order to understand better the PNP. Anyway, I don't want now to do this for all the actions, so just to show you this is just a visualization problem, it's not a problem with the execution. So here you see the main thread of the plan, that is just the conditional plan, and then what you can see is what the effect of the execution rules. So the execution rules, for example, what we added now is that if the condition not person here happens during answer, then this action is interrupted and the plan is doing the go to exit action. Sorry about that. And you can see this plan to increase complexity as during improvement. So what we really do, and you can imagine that with the real robots, these are even worse, the situation, because even here in simulation we have some problems with the robots, you have much more problems. But what you can do, and what is our strategy, is to challenge the plan and try to make it fail as much as possible, and try to find what are the recovery procedures. So we like to really stress the plan, because we are sure that the plan will fail. So we want to really test the plan and challenge the plan in order to prevent and possibly add all the recovery procedures for making the plan more robust, especially in cases like the ones that we are talking about, human-robot interaction. So it's absolutely necessary that we start with a conditional plan, with a good plan, but it is not sufficient. So that's why we need to improve robustness with these execution rules. Okay, I think that if you don't have any other question, of course, if you will have other questions, you can send us emails. On the website there will be the slides and this virtual machine, and of course our references, so you'll be you can contact us at any time. And maybe we have just a few final slides to conclude.
Really, just to wrap up and conclude. Okay. Okay, fine, thank you. Okay, just to highlight what we think are the main challenges in using planning for robotics and human-robot interaction. So first of all, no model is perfect, as we have seen, and we have to handle this issue, mainly because the environment can change significantly. So either because you have very hard environment like the underwater robotics, or like either because you work with humans, which are completely unpredictable. So also we need different models at different levels of granularity depending on the application domain and the kind of tasks you are interested in. And also we cannot expect to be planning only for fixed predefined goals, because new goals will arrive either solicited or unsolicited, or for opportunities, or due to some failure. So you need to recover, for example, if something fails. And also we like to have the robots reflecting on the performance and perhaps to be able to notify when there is failure, so new goals need to be added to your program and you need to replan for something that the robot itself is discovering. Some challenges for the planning community. First of all, when we do planning, we often risk to be too optimistic in the assumptions we make. So for example, we assume to know many things that we don't actually know. So a challenge for our community is to understand what are the reasonable assumptions we can actually make when we build our models. And similarly, we are too optimistic about the assumption about humans, right? They are much more unpredictable than what we think. And we need to handle them, as we have seen in the second part in the demo, also using conditional planning. The key point of planning is that plans are correct by construction, assuming, however, that the model is correct itself. So we need to do some work on how to handle domain validation, because if you have a wrong model, the plans you get will be correct with respect to the model, but not correct in reality. So we need to also work on model validation. And also, in persistent autonomy and more in general with robotics, plan validity is critically affected by temporal uncertainty. Things about the underwater domains, currents can affect the duration of the AUV moving between waypoints, or even interaction with humans can delay a whole task. So we need to be able to handle temporal robustness of our plan, whether a plan is still valid even if the duration of actions are different from what we anticipated. And also there are many cases where you don't want full autonomy, right? But you want supervisor to accept or to reject plans. And we need to be able to make plans clear to humans so that human can say, yes, I accept this plan, or I accept part of this plan, or I reject this plan. And similar link to this, we might work with not just using a full plan, executing the full plan, but we also interact with the user so that the user can decide to only execute part of the plan that we created. And similarly, we can have humans wanting to take less or more risks, so perhaps instead of generating single plans, we should also think of generating sets of plans so that the user can then choose one. There is some work in this direction on risk-aware planning. I think the summary for us is that planning for robotics and HRI is challenging, but it's also needed, right? And there is a lot of fun there. I think Luca wants to advertise this. You want to say more about this?
Well, this is something that's probably interesting for people who are here. So HRI is
you can take
yeah. HRI is a discipline in which we believe that AI in general, and of course planning in particular, is very relevant, because when a system, and a robot in particular, has to interact with humans, many assumptions that you do in robot environment interaction are not acceptable in robot-human interaction. And so this means that AI is very important for HRI, but at this moment we have a situation in which in HRI conference there is very little AI, if not at all. Especially the experimental protocol of HRI systems is using this Wizard of Oz modality, in which there is a person teleoperating the robot. And well, of course, it's good that HRI people, or some people from HRI are doing experiments on some other aspects of the system that do not involve real autonomy and real robotic operation. But on the other hand, the outcome of these investigations, of these experiments, are very optimistic, because the user is evaluating not the robot, but the robot with the mind of the teleoperator that is actually doing the right thing at every time. So I would say this is a very optimistic evaluation of HRI, because when a real robot in an autonomous mode will interact with a person, there will be many failures that are not evident when a robot is teleoperated. So this is I think the fourth workshop in the series. And also another workshop that has been already announced will be tomorrow is Plan Rob, in which here we intersect planning and robotics. Here we are intersecting AI and HRI, okay? And maybe in this tutorial we are intersecting planning and HRI. So I think that this is a good opportunity to continue discussion about AI and planning for HRI, and if you are interested even in contributing, the submission is due in about 1 month. That's the end. Okay, thank you very much for your participation. I hope that this will give some inspiration to you. At least you can try the demos if you are willing, and of course we'll be available for any question and any follow-up of this talk. And for sure this is not the solution, it's just the beginning of something, and we'll keep on working on these topics. So I hope that we'll meet again in some other moment. Thank you.